and for Krisp. Today I will speak about speech enhancement in challenging conditions. That is the content of my presentation. So we will give a definition of speech enhancement, some historical background, then we will speak about deep learning in the speech enhancement direction. Then we will talk about challenges and always to handle these challenges. And eventually we will give evaluations for our algorithm. So we all spend a lot of time in noisy conditions, and it affects the quality of speech communication. Particularly, it can make our voice less intelligible. So we need a tool which will remove the noises and keep human voice untouched. And that is what exactly speech enhancement can do. So more formally, in time domain, we have a speech signal and background noise. They edit together, and we have a mixture, which is the noisy signal. And the goal of speech enhancement algorithm is to reduce or completely remove the background noise and keep the human speech untouched. Speech enhancement also can be referred to as noise reduction, noise cancellation, and sometimes speech separation. And let's list some applications of speech enhancement. So, first one is obviously it is crucial having speech enhancement algorithm in audio communication systems. Also, it can be as offline audio editing tool. Another interesting application of speech enhancement is improvement of audio processing algorithms like automatic speech recognition, speaker identification, etc. And the improvement of these algorithms with help of speech enhancement is done in the following manner. So we take the input signal, we pass it through the speech enhancement, then we take the enhanced audio and give it to these algorithms. And the research and our own experiments show that by this way, sometimes we can have significant improvements of quality for the audio processing algorithms. And last but not least, speech enhancement used in hearing aid devices. And it turns out that reducing noise can significantly help to people with hearing impairments. So let's better understand the structure of noises. There are two types of noises, stationary and non-stationary. So the first one, stationary noises, actually has a simple structure. Their characteristics are mainly constant during time. For example, fan noise, white noise, etc. And the next type, non-stationary noises, are more complex one. So and also they are widespread noises, and they have time-varying characteristics like traffic noise, keyboard typing, pizzeria, crowd noises, etc. To measure the level of noise, we use something noise ratio, which is just the ratio of energies of speech and noise signals. Also, we use the dB scale, which is the logarithmic scale of sum to noise ratio, and particularly 0 dB means that we have equal levels of speech and noise. And some historical background. Note that first results in the direction of speech enhancement were obtained in 1970s, and here you can see some of them. So actually these results are based on statistical approaches and mathematical modeling of the problem. And they have some approximation, they give some solution. Let's have a closer look on two of these traditional approaches. So first one is called Spectral Subtraction algorithm. The idea behind this algorithm is that it takes the spectrum of the noisy signal, computes the noise model by sometimes taking the average for several segments of noisy audio, and then having this noise model approximation. It removes that model from the noisy speech and results in clean speech. The drawback of this algorithm is that it is not applicable for non-stationary noises, and in some cases, when we have non-stationary noises, it can even degrade the speech quality. The next type of traditional approach is adaptive noise cancellation. So the idea of this one is taking several sound sources, compare them with each other, and estimate the noise source, then adapt this noise source to the main primary signal and subtract it from that signal and get more quality speech. So with respect to previous one, this gives high accuracy, high quality for speech enhancement, but it has a huge drawback. It uses more than 2 sources, which is technically difficult because in many cases we use just one single source of audio, which is called monaural audio case. And so this adaptive noise cancellation has more narrow use cases. And from now on, by saying speech enhancement of audio signal, we will mean the speech enhancement of monaural audio signal, which is actually the more challenging case. So now let's talk about deep learning in speech enhancement direction. So it is well known that deep learning techniques overcome the traditional classical approaches, and it is true also in this direction. Here you can see the ordinary block diagram of speech enhancement with neural networks. So we have training and inference stages, and now let's pay more details to these blocks. So first step is raw data collection. So we have a big data set of speech signals and noise recordings, and to generate the training raw data sample, we randomly pick clear speech, then randomly pick the noise signal, mix them with randomly chosen sound to noise ratio, and we get noisy clean pair. Next step is feature extraction, and actually the common features for this direction is power spectrum. Let's quickly recall the definition of power spectrum. So we have discrete time signal xn. We use discrete Fourier transform to get Fourier coefficients, denoted here by xk. So xk represents the frequency domain for this signal, and then we use inverse discrete Fourier transform to go back from frequency domain to time domain. And here the square of xk is called the power spectrum for input signal. And next, by taking the neighboring time segments power spectrums, we get the spectrogram. You see here an example of spectrogram. It is actually a color map for power spectrum values for frequency and time dimensions. So in this picture, each point shows the value of power spectrum for given time and frequency. And the light color means high values and vice versa. So actually the spectrograms and spectrogram-based features are widespread for audio processing algorithms. Now, let's talk about neural networks. So, practically each popular neural network architecture can be tuned in order to be used in speech enhancement problem. So, so that we can use spectrograms, which are actually pictures, and convolutional networks work well on pictures. Also, speech signal can be represented as sequential data, and hence we can use recurrent neural networks, and also we can use deep and dense networks to obtain relations between audio patterns, so complex relations. In our case, we have tried a lot of neural network architectures. We have tuned these architectures, experimented with them, and actually we came up with our own neural network architecture. So generally visualizing our problem, so we have the following picture. We take a noisy speech spectrogram, give it to the input of our neural network, and in the output we get the approximation of speech and noise spectrographs. And then applying post-processing techniques, we go from frequency domain to time domain and eventually obtain the cleaned version of speech waveform. And now let's talk about challenges. And let's have a look at audio communication pipe flow. So, audio signal is generated, then passed to the microphone, then conferencing up, and is transmitted with Internet protocol to the receiver conferencing application, and then it is played by loudspeaker at the receiver end. And our noise cancellation algorithms are working in these two nodes, as you see. So first one on top of the microphone, and the next one before the loudspeaker. And this pipe flow shows the potential points for challenging cases and audio degradations. So first one arises in the heart of audio signal generation, and it is due to acoustics of environment, and is called reverberation. The next one, which I would like to mention, is called packet losses, and it arises in the step of internet protocol, and can be as a result of bad internet connection. So, we fixed two audio degradation cases, reverberation and packet losses. So, what about the impact of these degradations to speech enhancement algorithms? The experiments show that they can affect on the speech quality after speech enhancement. So they can degrade the speech quality, and other issue is the decrease of noise cancellation quality. And our approach to solve this problem is data augmentation. And now let's bring more details about this degradation. So reverberation actually is the phenomena of audio signal reflection from the walls of the room and other reflecting objects. And here you can see in the picture that reflected signal is added to the direct signal, and we get reverberation. So the form of reverberation depends on the form of the room, the material of walls, other reflecting objects, and also the location of sound source and listener or microphone in the room. And the strength of the reverberation is proportional to the microphone and sound source distance. And let's quickly recall the properties of reverberation. We know that it is a linear and time invariant system, which means that we can represent the reverberated signal Yn as a mathematical convolution of input signal Xn with special signal called room impulse response. And below you can see the definition of room impulse response. So actually it is a reverberation of a simple signal called delta impulse. You can see it in the brackets. And the room impulse response fully characterizes given reverberation. So, and the second formula here gives us a way for reverberation augmentation. And to measure the reverberation, there are two effective metrics. First one is called RT60, which is actually showing the duration of reverberation. And the next one is direct reverberant ratio, which is the ratio of direct and reflected signal energies. So here you can see the room impulse response example. As you see, it has a tail-like form, and here you can see the spectrograms for clean speech and its reverberated version. And I would like to pay attention on the stretched lines in reverberated speech spectrogram. So it is due to the tail-like form of room impulse response. So, and actually, you see that reverberation is a type of speech degradation. And now let's talk about packet losses. So as we already mentioned, packet loss can arise in case of bad internet connection. And there's a popular model for simulating packet losses. It's called the Gilbert-Elliott model. and it describes packet losses as Markov chain model, Markov process, which means that the probability of each event in this process depends only on the previous state of previous event. So here we have two states, non-lossy and lossy, and you can see transition probabilities P and Q. And for example, if we want to simulate aggressive packet losses, we want to lose many audio frames, then we have to increase the probability P and decrease the probability Q. And below you can see the example of state sequence for packet losses. And so when we have such sequence of packet losses, we can apply it to the spectrogram, to the features of audio, and here you can see some example of application. We have original spectrogram and we have lossy spectrogram, and as you see, these black parts actually are lost packets. So, as I already mentioned, to solve these problems, we use data augmentation, but there is a huge trade-off in this approach. It is the following. So we want to make our algorithms and degradation robust in these challenging cases, and at the same time we want to keep the quality of our noise cancellation algorithm the same in ordinary cases. So we have done a lot of experiments. We tried various proportions of data augmentation, and eventually we came up with the following numbers. So we augment the reverberation by 0.2 probability. So we have the huge data set of room impulse responses which represent various rooms and acoustic conditions. And each time when we introduce a reverberation, we randomly pick one of these room impulse responses and apply it on the raw data sample. Then we apply packet losses by 0.1 probability, and we randomly choose transition probabilities between states of packet losses from these values. And actually these are the values, reasonable values for simulating real life scenarios of packet losses. And as a result, we have monaural speech enhancement algorithm designed with special design neural network. It is robust to audio degradations, which we already mentioned. And also, one important thing that it is real-time working. So we have only 15 milliseconds of algorithmic delay and no look ahead. And eventually, it is computationally efficient, which is a crucial point. And we use for about 20% of CPU for a single core. And if you haven't tried our algorithm, you can visit our website and try it. It will be a natural demo for you. Now let's talk about evaluations. We use perceptual objective of listening quality as evaluation metric, which is the recommendation of International Telecommunication Union. And let's see how this algorithm works. So it takes the target signal and the original clean speech signal along with that target signal. Then, based on special psychoacoustical mathematical model, it returns a score between 1 and 5. So, for example, when we have degraded speech and noise in that signal, and we take that degraded speech along with the original clean version of that speech, in that case, the polka will return probably bad score, near to 1. And on the other hand, if we take the original signal with itself, it will give score 5. And so the better the quality of target signal, the higher will be score, and vice versa. And now let's see some evaluations for our algorithm. So here you can see the evaluation scores for our test data set. So we have a huge test data set of various noises, speeches, and degradations. And here the bars are taken for given noise type. And actually the bars show the average score for the given noise type. And here you can see that on each noise case, when we apply speech enhancement to the input audio, we get the improvement of quality in terms of polka evaluation metric. Also note that one advantage of polka is that it approximates the scores of of human listeners. So it approximates the mean opinion score of listeners, and if we take a graph of people and give the same task for scoring the quality of audio, probably they will give the score in average near to polka score. Also, note that we constantly do comparisons with our competitors, and here we can see one of them. So here we compare our noise cancellation algorithm with NVIDIA's noise cancellation. So as you see, there are some cases where scores are comparable in some noise types, but at the average, our algorithm shows a superior result. And that's all. Thanks a lot.
So now we have time for questions. Do you have questions?
This question sort of stems from the previous talk. Since you're formulating, at least partially, the problem as a computer-driven problem with a spectrogram test picture itself, have you tried using like other approaches from vision? Maybe like the transformer or like Cancellation or using Enhancement?
Currently, we are trying to use new architectures, new architecture for problem. We actually tried some unit-like structure. We added recurrency in the unit, and we obtained the comparable results to our other networks. And now we are just trying new architectures, hoping that we will overcome our current scores, our current neural network architecture.
You mentioned about both methods, that one of them is combined two different sources. For example, like we are in gates, and I wonder what's the practical distance between microphones that would provide a certain improvement of the method, and whether in certain applications this neural network ML technology can be combined with the difference or combination of different sources to give even better results, of course, for subset of problems.
Okay, so in case of different sources, actually the problem is different because the logic of that algorithm is to evaluate noise models, so to adapt the signals and get the noise model. We haven't tried to take as an input several sources because once a single source is more challenging case. The distance in our case for our algorithm can be, for example, 1 or 2 meters on the microphone. But it is a very challenging case because when you increase the distance between microphone and signal source, you get high reverberation, high degradation, and it is more challenging working with scenarios. I guess the distance should be between somewhere from 10 to 15 up to 50 centimeters. Let's see. I guess applying neural network will give even more accurate results for several sources. But it is not our case, that's why we didn't try. But if you are interested, you can try. I think it will give better results, and actually you can obtain results by using very small networks, which can even be integrated in hearing aids. Because the complexity of the problem is not as difficult as in our case.
Yeah, I wonder because like these technologies, Swedes, German, and other companies, they are already integrated in these technologies, but this is a new arena, and maybe this can go and disrupt this industry as well.
Thanks for the question.
Thanks for the great speech. So you mentioned that there is a lag or delay of about 15 milliseconds. Could you just describe how much in percentage of it comes from the pre-processing stage of the audio, like the Fourier transform, and how much comes from the model itself?
So it just comes only from pre-processing and post-processing techniques. Our models succeeds to work within one frame time, and it is real-time working technology. So the delay is due to the audio segments overlapping structure. So to obtain the cleaned segment, we need to overlap the neighboring segments, and that's why we have to wait some short period to get the cleaned audio frame and put it with the previous segment. So it's just pre and post processing delay.
Yeah, first of all, 15 millisecond latency is a great number, so good job, guys. The question is this, do you guys have technology where you have user-led training process, where you just recommend individuals or users' voice versus just separating the background noise?
So currently we also working on the algorithm called personalized noise cancellation. We also had a prototype of this algorithm, and the idea of it is the development of noise cancellation and the next level of noise cancellation, which actually gives a model for specific user, and in that case it keeps the voice of the specific user and removes the other voices, other human voices, and also noises media.
So, is there any time frame when it will be released?
I guess so short period it will be in release.
I have one question. So it is known that human voice contains 4 months, so-called 5 regions with a little bit high level of energy in a spectrogram. So do you use these kind of things in order to differentiate noise from the human voice, or basically to detect is it human or not? On your spectrogram, it's very precisely can be seen this kind of formats. Yeah, for example,
These slides, yeah.
So here, 1, 2, 3, 4.
Yeah, those are the fundamental frequencies with human speech. So we developed special algorithms which distinguish between human speech and noise. We have also voice activity detection algorithm, which actually shows the short audio signals where human speech exists. But in our case, I guess if future set is diverse enough to allow neural network distinguish between human speech and noise. And actually, we try to put the classical approaches with neural network, and also we tried without the classical approaches of distinguishing between speech and noise, and we get the same result, comparable result. So we use those techniques for another purposes. The noise cancellation is mainly done by the good choice of features, good post and pre-processing, and reasonable choice for neural network.
I guess no other questions. Thank you very much for presentation. Now we have a small coffee break for 15 minutes, so we can proceed to the cafeteria.